So, then welcome to the year 2025 and to lecture, I believe it's number 11, in Introduction to Lattice Boltzmann method, and we finally arrive at the real thing, how you should implement, how you should do Lattice Boltzmann with the Cumulant MRT method. So, today we'll learn about first central moments, then the problem of Galilean invariance, and finally we'll implement our Cumulant method. Okay, we have a lot of ground to cover today, so let us start with the conclusion from the last lecture, where we had seen the problem with MRT. So we had an MRT method, multiple relaxation time method, with non-orthogonal moments, and we had one with orthogonal moments. And then we had recognized that in both of them we'll have problems with the ghost moments, and in order to get rid of these problems with the ghost moments and actually allow really different relaxation rates for the ghost moments without crashing the code, we needed to have a particular moment, namely the 1M211. We had to make this weighted orthogonal to the moment M011. Now, one thing that is important to understand why these things are difficult to figure out is or have been historically difficult to figure out is, as you see, this moment that makes here trouble, M211, is a moment that only exists in 3 dimensions. It does not exist in 2 dimensions. Yeah? So this particular problem that you see here will only show up in 3 dimensions. And what mathematicians and people who started with Lattice Boltzmann like to do is they study the theory. Most of them like to study the theory in 1D first, yeah, which probably doesn't make a lot of sense. Then they go to 2D, and then they study everything in 2D, and then they think you just scale this up, yeah, in 3D, and you have the same property. So this is not true. You cannot see this kind of problem in 2 dimensions, yeah, because just this moment does not exist. So anyway, there are also other problems that we can see in 2 dimensions with this, and this is a little bit what we are going to see today. But as a caveat in the beginning, I have to say that you really only see the real difference between MRT, weighted MRT, and cumulants that we are looking at today only in 3 dimensions. Yeah? So in 2D, there are few differences, but these differences are very small. In 3 dimensions, they are really drastic. Yeah. Okay. So we saw that there is this problem, and the question. So two questions that we ask now is whether this now was the only problem that we had to observe here. Yeah, so we found a problem. Is this the only one? So is there further dependencies? On other moments? Because we only found this particular one. And something that we have not yet covered is also thus the frame of reference. So this is basically the main question that we'll discuss today. The frame of reference matter. So we found that orthogonality matters, but also what does this mean for the frame of reference? So what do I actually mean by the frame of reference? So look at the classical MRT. And this MRT could now be orthogonal, non-orthogonal, or weighted orthogonal, whatever. They use so-called raw moments. So raw moments are moments taken in a fixed frame of reference, which we call the Eulerian frame. So a moment, so this kind of velocity moments, they are integrals over a polynomial in velocity, right? And this polynomial in velocity has to be stated in a particular frame of reference. Yeah, what is velocity 0? Yeah, so you integrate over velocity polynomial given stated in a particular frame of reference. And this frame of reference is the resting frame of reference. This is, so to speak, that the lattice velocity, the non-moving particle in the lattice velocity has velocity 0. Yeah? So the lattice is at rest. Yeah? This is what it means. So this is say it is a fixed frame. Okay, so there is an alternative to this that we can call central moment. Central moments, MRT. By the way, this is so to speak my firstborn scientific child. So this is, I developed this in my PhD thesis using so-called central moments instead of these raw moments. So what's the difference? We are now in a Lagrangian frame. In a Lagrangian frame. And this is the material frame. So the material frame is, say, we calculate the moments not in the frame of the lattice, but in the frame of the fluid. Yeah, so the fluid is moving, the fluid has a velocity, so we state these polynomials in the frame of the moving fluid. So we have to calculate the velocity and shift the coordinate system into the frame that is co-moving with this velocity of the fluid. So then these two things can be distinguished like this. So let's state again the raw moments, which are the ones that we have been using all the time during the last few months. So this is the Eulerian. So here we have the moments M, A, B, C is the sum over I, the indices I, J, and K, and I by the power of A, J by the power of B, and K by the power of C into F, I, J, K. Yeah, so this is, you should now be very familiar with this. Yeah. So, and in contrast to this, there is the central moment. In the Lagrangian frame. And to distinguish them from the raw moments, we use the letter K. Yeah, AK, ABC is the sum over I, J, and K, with I minus ux by the power of a, j minus uy by the power of b, and k minus uz by the power of c, and this into fij k. And I took the liberty of the simplification that we state the velocity in lattice units. So this is the simplification that we say that ux, the dimension of ux is 1. So this means that the velocity is 1 when one particle is moving from one lattice side to the next lattice side in one time step, right? Just in order to simplify the notation a bit. Okay, so how do we know these velocities? We know the velocities by stating that the central moments k 1, 0, 0, or let's say so the k. Okay, you give me the answer. If we are in the frame of reference of the moving fluid, what is the first moment k 1, 0, 0?
It's going to be I1 minus 0. Is it 0?
No, it's the velocity of the fluid.
And it's 1.
Then it's 1. The k1, 0, 0 is 1?
Oh, wait, so
No.
j minus u.
Okay, no, you have to determine from the flow. So f, you have to determine from the flow, from f. These velocities are determined from the flow. They are not external parameters.
I get it. So
Yeah.
it's going to be the sum of I times I minus ux.
Yeah, but you are thinking too complicated. So k1, so what, first moment, what is m1, 0, 0?
It's rho times u.
ux, yeah?
Yes.
So now if you are if you calculate the velocity of, or the momentum, yeah? So if you are in the frame of the moving fluid, what is the momentum then?
If you're in the frame, so isn't it going to be rho times u minus ux?
So it's rho times ux minus ux. So which is
U minus it's 0.
it is 0, of course. Yeah, by definition, these things are 0, and this is the way. So if you wonder how you determine what is ux, you determine what is ux by setting ux such that k1, 0, 0 is 0. Yeah. So this is what determines what ux is, and this is true for all the first order central moments. They are all by definition, yeah, 0. Okay. So then there is, which I state without any proof, there is a method to determine moments, or to transform moments from one frame of reference to another frame of reference, and this is the binomial transform. Is actually this works for changing any frame to any other frame, so it's not necessary just for central and raw moments, but I'll state it here for the central moments. So the central moment K, A, B, and C is the sum over alpha from 0 to A into the sum over beta from 0 to B into the sum over gamma from 0 to C, A over alpha, B. Okay, I don't know what is the right way to say this. So these are the binomials. I'll write the definition in a second.
Combination?
Yeah, the combinatoric, yeah. A minus so minus 1 by the power of A minus alpha B minus beta plus C minus gamma. So there's a lengthy equation. It doesn't fit into one line, so I'll multiply this here with the, now comes the Ra moments, M alpha beta gamma, M10 divided by M000 by the power of A minus alpha, M010 divided by M000. So you see this is the velocity, obviously, yeah? B minus beta, and this is M001 divided by M000 by the power of C minus gamma. Yeah, so this is the binomial transform between different frames of reference, and the binomial I have to look these things up. So A over alpha is equal to A factorial divided by alpha factorial times A minus alpha factorial. Okay, so this is how you, given you have Ra moments, you can calculate central moments. And by the way, I have to say this in the beginning, this is how you can do this. This is not the best way to actually do it, yeah, but it is a possibility to do it, okay? Okay, let's look into the 2D case. So what does it mean for example, K20? K20 is M20 minus M10 squared divided by M00. I mean, you can easily see how you make this here to a two-dimensional case. Just skip over the one part. Okay, so this gives us M20 minus UX square rho square divided by rho, obviously, which is, of course, M20 minus UX square times rho. Yeah? So this is, you see, you get simply K20 is simply M20 minus UX square and UX square times rho, and very similar, K11 is, okay, can you give me a guess what is K11 in terms of Ra moments?
It's going to be M11.
M11 minus.
It's a guess, right?
It's a guess, yes?
It will be UX squared.
UX squared?
Or UX times UY.
Okay, that sounds better, times rho. Okay, it's easy to guess it.
Okay.
Yeah? Okay.
So it's going to be the rho moment minus the equilibrium.
Not necessarily. Not necessarily, yeah? But it is, in this case it is, yes. So actually it is not in M, so actually for M20 it's not. Yeah, because, okay, this is actually what I wanted to continue with. What is M20 equilibrium? M20 equilibrium has two components. It's UX square, and then you remember that there is this temperature, theta, yeah? So you see, there is only one part of it. Yeah, so now if you plug this into this, so okay, give me a guess, what is the equilibrium now of K20?
It's going to be M20.
Yeah, M20 equilibrium minus this part, and then what is left?
But what are you using this equilibrium? If the gas M20 using this equilibrium, or if
so I mean so it will be M20 equilibrium minus.
UX squared.
Okay, it's easy to see. So it's this equilibrium minus this.
Which one?
This one.
Okay. I see.
Which is?
The CS or the theta times rho.
Theta times rho, right. So M11 equilibrium. So M11 equilibrium is just Ux, Uy, rho, and then obviously this means for K11, which is 0, right. So as you see, it may depend on the density, these moments, but their equilibrium never depends on the velocity. Oops. Not a function of the velocity, So everybody's still awake? Okay. So, and now, what is this actually good for? The idea behind this was to actually implement something that's called Galilean invariance. Or to deal with the problem of Galilean invariance. And what is actually Galilean invariance? The idea is that in physics there is no special reference frame. So frame of reference must not influence the behavior of the methods. So previously I taught physics, and when you teach physics you always think you're teaching stuff that is true forever, yeah? And in the past we always said that there is no special frame, special inertial frame of reference in the universe, yeah? And so we could take any frame of reference. So this was before they measured the cosmic background radiation. Because the cosmic background radiation, unfortunately, gives you a specific frame of reference of the universe because it can move against the cosmic background radiation. So there actually is a special frame of reference in the universe, unfortunately, after so many years that we always said that this is not possible. Okay, but this effect is very small. So now, yeah, what we want to have is that the frame of reference in which we state our method should not matter. So first of all, we have to recognize that this is not possible because we are on a discrete lattice, velocity lattice. Yeah? So it will be impossible to develop a method that does not, in some sense, depend on the relative velocity of the simulated fluid against this lattice. Right? So you will have discretization errors because you discretize the velocity space. Now the question is how to make these discretization errors as small as possible. Yeah? This is of course, so you will always have them, but you want to have them as small as possible. And for this, we actually look at whether doing the collision in the Eulerian or the Lagrangian frame of reference makes a difference to begin with. Yeah? Because now we always live very well with this MRT method that does the relaxation in the Eulerian frame of reference. So what's the problem? Yeah? So let's see what is the problem, whether there is a problem. Let's say we do the relaxation of Ra moments, so we do the usual MRT stuff. And just rewrite everything into central moments and see whether we observe any dependence on the velocity, which we don't want to see. Okay, our collision operator, let's start with the second moments because they are the important ones. M20, yeah, so never mind that you would usually do this splitting between, the sum of the second moments and the difference between, never mind this now. Just say we have the post-collision state is the pre-collision state plus some relaxation parameter for this particular moment into the equilibrium minus the pre-collision state. Okay? So now what we simply do is we replace all these Ra moments by their equivalent central moment. Yeah? And see whether in central moments we get the same equation. So what we have to do is we have to write K20. So, and now we said that K20 is M20 minus the velocity. Now we'll have to bring this to the other side and see that this is plus ux square rho. So we'll have the same thing on the other side where we do the same thing with the pre-collision state plus ux square rho plus omega to 0. Now in equilibrium, here comes the equilibrium of K to 0 plus ux square rho minus K to 0 minus ux square rho. Now, obviously, you see that this here and this here will disappear together, and that this and this together will disappear, so that you can say this is K20 after collision is K20 before collision plus omega 20 K20 equilibrium minus K20, which is what we wanted to see, right? So this second moment, no matter in which frame of reference we relax it, will always give the same equation. Yeah? So that's a strong indicator that MRT does it right. So do you believe that MRT does it right? I mean, why are we talking? Yeah. So let's notice that, I mean, one thing for sure. In principle, so MRT does not do it. I mean, it is not completely wrong. Yeah. So it gives you a reasonable result. So it cannot be completely wrong. Yeah. So because if this was not the case, then it wouldn't work at all. Yeah? Okay, so for second moments, because you remember, we have to get the second moments right. Yeah? We have to get them right. Order moments. So K20, K02, and K11. Now we have the problem that there are so-called ghost moments, and you remember that the ghost moments, from an asymptotic point of view, such that you converge to the Navier-Stokes equation, do not necessarily need to be correct, or at least they only need to be correct to first order. Yeah? Yeah? So, but what happens there? So let's see third moments. So third moments are the first growth moments. So say K21 is equal to M21. What am I writing? M21 minus ux, so this comes from the binomial transform, 2 times ux m11 minus uy m21 plus 2ux square uy rho. Now, you see, there is something interesting going on here, because this guy, or these guys, they are collision variant. So they are not. So in the definition, yeah, there is something that changes during the collision. Yeah, these moments are not conserved. Yeah, this here is invariant under collision. Could this cause any trouble? Okay, let's see. We want to express the raw moments in terms of central moments. So, but in here, so there is dependence on several moments. So we'll have to write here things down again. So M11 is K11 plus UX uy rho. M20, which exists here, is K20 plus ux square rho. And now if we solve for M21 and enter M11 and M20, yeah, we'll end up with M21 is equal to K21 plus 2 times ux K11 plus uy K20 plus ux square uy square. So I now put this from my notes. I hope I've done this correct. So we'll have, let's see. So we'll have 2 times the stuff here. So we'll have it one more time here. So this gives it 3 times. So it will be minus ux and ux square uy, and then we put it to the other side. So I would say this is correct. Yeah? Seems correct. Okay. Okay, so let's do the relaxation of M21 in the Euler frame. So unfortunately, we have, you need more paper because we have a few things to write. You need more pens. Okay, I see. Okay, so what we want to look at is the relaxation of this moment, which of course looks like this. So there's an omega related to this particular moment, which we call now omega 21 into M21 equilibrium minus M21. And now we replace all of them with their equivalent parts in central moments. Of course, there is, you already noticed that there is a few lines to write here. Yeah, so it's K. So first of all, the left-hand side. Yes, all post-collision. K21 post-collision plus 2ux. Now, of course, this K11 is obviously also post-collision, right? So it's K11 post-collision plus uy K20, obviously post-collision, plus ux square uy rho. So this is what is on the left-hand side. Now this is equal to what is on the right-hand side is the pre-collision. Yeah, so it's all the same, just in terms of pre-collision. Plus uy k to 0 plus ux square uy rho. And then comes the omega to 1. And now comes everything the same, just in terms of equilibrium. K 1, 2 equilibrium plus 2ux k1, 1 equilibrium plus uy k2, 0 equilibrium plus ux square uy rho. And now comes minus m2, 1. So everything again the same, just changing the sign here. K2, 1 minus ux k11 pre-collision, uy k20 pre-collision minus ux square uy rho, and closing the bracket. Okay, what we notice immediately is that this here, these two things here all disappear. The same thing on the left-hand side, on the right-hand side with these guys, but otherwise, there is a lot that remains. So, and in particular, one thing that remains is these post-collision states here. Yeah? So, what do we do with the post-collision states? So, we'll use we know what the post-collision state is, so this is K20. We notice that this does not depend on the frame of reference. It can simply write it like this. And also K11 after collision is K11 plus omega 11 K11 equilibrium minus K11. So, which means if we introduce this in the above, we get K21 after collision plus ux omega 11 into K11 equilibrium minus K11 plus uy omega 20 K20 equilibrium minus K20. And this, so this was just the left-hand side. The right-hand side is K21 plus omega 21. You can write K11 equilibrium minus K21 plus 2 times ux K11 equilibrium minus K11, so this is something that we see above there too, plus uy K20 equilibrium minus K20. Okay, let's close all the brackets and just rearrange this a little and put so that we have only K21, this is the thing that we want to have, only this on the left side, bringing everything else to the right side, is K21 plus omega 21 to K21 equilibrium minus K21. So this is what we want to have, right? This is the Lagrangian frame. So, but this is not all we have. In addition, we have, so, I mean, the relaxation of the third order of if we do a collision in the frame of, in a centered frame of reference, yeah, so in the frame in which the velocity is 0, we don't want to see the velocity at all. Yeah, there should not be any velocity. So what do we get? Of course, we get velocity. Yeah, velocity did not disappear. So we have velocity omega 1, omega 2, 1 minus omega 1, 1 into K11 equilibrium minus K11. I mean, you know that K11 equilibrium minus K11 in general is not zero. This is the stress. Yeah?
Here I have a question because K11 equilibrium was 0, right?
Yeah, so what?
So.
But K11 is not.
No, so it's going to be ux times those omegas times K11.
Yeah.
Okay.
Plus uy omega 2, 1 minus omega 2, 0, K2, 0 equilibrium minus K2, 0. So you see that K2, 0 equilibrium is not 0, right? So, and this, all of this is in violation, so this is incorrect. It's in violation of Galilean invariance. Okay, let's state it again. What is Galilean invariance? To make this very clear, Galilean invariance so any law of physics, by the way, of course, if you are in a physics class, they will tell you there's no Galilean, you should, laws of physics are Lorentz invariant, yeah? Because Galilean invariance assumes that time is running everywhere in the same way, yeah? So this is, Galilean invariance is already a simplification from classical physics, say, yeah? Not relativistic. But anyway, the idea is that any law of nature must be independent of the inertia frame in which it is stated. So inertia is important because if you are in an accelerated coordinate system, of course you feel something. Yeah? Like we are on Earth, so you feel the Coriolis force. So it makes a difference whether you are in the frame of the rotating Earth or not in the rotating. But this is because it's an accelerated coordinate system. Yeah? So an inertia system is a non-accelerated coordinate system, and in any non-accelerated coordinate system, the laws of physics have to be the same. Frame of, what did I say? Now, we notice that this is not the case for MRT. Let's go to a new page. In the third order moment. So this means that MRT cannot be physically correct, yeah? Because nature does not allow this to happen. So a third order moments not Galilean invariant unless, so we can make these things Galilean invariant. Very simple, by deciding that these relaxation rates are all the same. Mm-hmm. Yeah, so if these relaxation rates, the second and the third, are the same, then they are Galilean invariant. And is this what we wanted? We wanted to have different relaxation rates. So this is why we call it MRT. Yes. Yeah? So unless omega 2, 1 is equal to omega 2, 0 is equal to omega 1, 1. I mean, there's a conclusion that some people really like, that BGK, of course, BGK is Galilean invariant. Because BGK is the case that you set all the reds to the same value. Now you remember our coding example, and you see that BGK is a lot less stable. So do we want to go back to BGK just because it has apparently this property, or do you think that BGK is necessarily the only way to make this happen?
I have a question.
Yeah.
What if another condition for it be Galilean invariant would be that K11 equilibrium is equal to K11, or K11 is going to be always equilibrium state?
No. Then it would be conserved.
So that can't.
No, I mean, it's. Yes, you are right that this. By the way, this is the reason why the second moment is the relaxation of the second moment is Galilean invariant. The reason for this is that it only depends on conserved moments. So if you make K11 a conserved moment, if you make all the second moments conserved moments, then you can relax the third order moments, and they will be Galilean invariant. The problem is that they depend on something which is not conserved. This is the basic problem. Yeah. Okay, so okay, we have to make a very important realization here, namely that I was talking about that lattice Boltzmann will never be Galilean invariant because we have a discretized velocity space. However, so my internet, do you still hear me? Because there's the frame froze.
You are frozen, but we can still hear you.
Okay, yeah, that doesn't matter. I look strange frozen, but anyway, yeah, it will always freeze. Yeah, so I was saying that that because of the discretization of the velocity space, we will never be Galilean invariant, right? However, in the example that we looked at in the third order moment, we did not use this discretization. Yeah? So this would be the case even if we had not been discretized. So even in the case of a non-discretized or perfectly discretized velocity space, we would still not be Galilean invariant in MRT, right? So this is very important to notice, yeah? So, because you can always say it's discretized, so this is not the reason. It's not the reason for MRT not being Galilean invariant. This means that the violation of Galilean invariance in MRT is worse than necessary from the perspective of the discretization. Okay. Let's just list these few problems of MRT that we now have kind of a little bit of a summary. So we had the problem of the ghost moments were not independent of each other, as we noticed. And this, even if they were, I put this in these quotations, orthogonal, Yeah, so we always had this dependency somehow. Anyway, so this has nothing to do with Galilean invariant, but in Galilean invariance. But on top of this, the ghosts are not Galilean invariant. So these are the two major problems with MRT. And these, by the way, are not problems of BGK. So, and this is also the reason why there are still people around that love BGK, yeah? Because MRT has all of these ugly mathematical problems. Here, so it's not a problem of BGK, but in this we have only a single relaxation time. Time or rate, I don't know, rate, time. So, do we want to stick to MRT or do we just to BGK, or do we notice that moments may not be the best choice or the best basis for MRT? So, let's look at something better, and the thing that is better that solves all these problems is using cumulants instead of moments. And this leads us to the cumulant method. More paper. Okay, what we actually want is that the variables, which are, okay, the moments are our variables, somehow observables, yeah? And kind of we get the impression that we have lots of problems with this moment, so we want to replace them by other variables, yeah? So let's just talk about variables, yeah? So variables, these variables that we are talking about, they should be independent of each other. Especially the variables that we want to relax with different rates, because otherwise their relaxation time or their relaxation times would be coupled. You see, if say the temperature and the duration of sunshine, yeah, is always coupled. Yeah?
Duration of what?
The duration of sunshine during the day, say. Yeah? If the temperature, if these things are always coupled, then they will change on the same time scale, right? So there may be a shift, and they may not follow each other exactly, but they will always move at the same time scale. So if you want to have things evolve at different time scales, as we propose by using MRT, then these variables have to be independent. They have to be uncorrelated. Yeah? So if they are, because if one follows the other, it will always also follow its time scale. Yeah? So then it's of uttermost importance that if we want to have different time scales and different variables, that these things are really independent of each other, not as in not correlated. Yeah? They don't follow each other. Yeah? So, and then we'll have to think about what what are the so-called, what does this mean, independence? So the guys who invented Lattice Boltzmann, so they said, okay, independence, we make variables, we make the matrix orthogonal, and then things are independent. Okay, so is this a good definition? We make matrix orthogonal and then variables are independent. Is a little bit, to me it's not clear what this means. Yeah? So, what it should mean if things are not correlated. Say we have two variables, we have two random variables, like the velocity of, okay, think, because we are already in kinetic theory, you pick a particle and you measure its velocity in x direction. Yeah? So, do you then know its velocity in y direction? No. Or do you have knowledge on it? Okay, what does it mean if you don't know? It means that they are independent, yeah? Which means that knowledge on the one does not imply knowledge on the other. This is what independence means, yeah? So if so for example, and this has to do with probability, yeah? So when I know that that there is a student and they study civil engineering, yeah, then I have and I know nothing else about them, then I already have a knowledge on their gender, even though they can be female or male, but the probability that they will be male is higher because they study civil engineering and not architecture. If they studied architecture, then the probability that they will be female would be higher, right? So it's about the probability, not that I really know, just that I have some knowledge on it, right? Okay. So, say knowledge of the state of X implies no knowledge. I mean, also in the statistical sense, no knowledge. So, no knowledge on the probability, that is, on the state of Y. Okay, so now we have to somehow find variables that have this property, yeah? And for this, we recall how we actually build our moments. Recall the moment generating function. So the moment generating function was this Laplace transform as a function of the the Laplace transformed velocity space, yeah, because we have a distribution function in velocity space. And the Laplace transform in this case is defined, so it's a bidirectional Laplace transform, so it goes from -infinity to infinity over the populations f with the velocity xi in the power of xi times e by the power of the actual velocity times the frequency velocity integrated over xi, and with all the unfortunate case that with regard to the original Laplace transform to the actual Laplace transform that you learn in the book, that there would be a minus here, and somehow in all of the definition it got turned around. Yeah, I don't actually know how this came, but you know, you can always define the Laplace transform this way or that way. So in principle, it's the inverse Laplace transform, if you will. Yeah. So yeah, this is not important. So this is this f is a function, of course, of all its moments. Yeah? So, and this is a probability, this f is the transformed probability distribution of finding a particle in frequency space. So, okay, so what do we know about probability distributions of joint probabilities of independent variables?
We know. Can you repeat the question? What do we know?
So we have, now we want to see a different variables, yeah? So we say our distribution function should be described by different variables that are independent of each other. So now then there is a joint probability distribution. Yeah? So what do we know about joint probability distributions of independent variables? That they can be factored. Yeah? Okay. So this is an important property that we are going to use. So independent variables mean that we have a factorization of distributions or the factorization of the distribution. So say we have this joint, the big F, yeah, that is a function of m of all the moments. Then we propose that we can write this thing as the product of individual probability functions that depend only on independent variables. Yeah? So we don't know what these independent variables are, right? So we just say we propose that there exists variables for which we can write individual probability distributions that, because they are independent, taken their product will give us the original F. Yeah? That is the same F. So it's the same thing expressed in different variables. So, right, so I just wanted to write this down. So if, say, Ci and Cj are independent, they are joint probability distribution factors into their individual probability distributions. Okay, let's again look at how we calculate moments. And in this, I remind you that we use this frequency velocity vector, which we have previously written as the frequency in x, the frequency in y, which we write by upsilon, and that in z, which we write by capital zeta. Yeah? And then we define the moments moments MABC. So you remember this is these derivatives. So the 8th derivative in Xi, the beat derivative in upsilon, and the C derivative in zeta of f of vector Xi, and this is taken at the development point for Xi vector equal to 0. So this is important to see that the moments are the coefficients of a series expansion. It's not really the Taylor expansion because we skip out a factor, yeah, but we can write this equivalently as a Taylor function. So we can write f of Xi can be written as a sum, because it's the sum of these guys, A, B, and C. So a sum over all the moments from 0 to infinity gives us the, yeah. So if we make a series expansion of the of capital F, then we can write capital F in terms of this coefficients of the series expansion, and this will be Xi by the power of A. Epsilon by the power of B, zeta by the power of C, divided by, so this factor A factorial, B factorial, C factorial that has been missing, times the moments MABC. So this is how we get from the moments to the probability distribution function in a frequency space. But these are, of course, not independent moments. Now we want to have these things to be written in independent moments. So how to do this? For independent moments, not moments, I mean variables. So say there should be independent variables. And we say that f of Xi is defined as being the product from I to infinity of individual probability distribution function Fi that only depend on Ci. So now this one guy is in form of a sum and the other guy is in form of a product, right? So in order to get this into the same format, what we have to do, I mean, in order to write this down here in the same way as we write this down here, we have to use the logarithm of this. Yeah, to turn a product into a sum, we use the logarithm. So if you write logarithm of f of this Xi, then we get the sum I from 0 to infinity of the logarithm of Fi of Fici. So, and this now has the same form as the original definition of the moment. So what we define the cumulant generating function being the logarithm now of the moment generating function. Yeah, logarithm of the moment generating function, and this can be written as the sum over A, B, and C from 0 to infinity over Xi by the power of A, epsilon by the power of B, zeta by the power of C, A factorial b factorial c factorial. So we propose, yeah, that the logarithm of the moment generating function can also be developed in terms of some quantities, and these quantities, by means of the definition, will then be independent of each other. Yeah? So C, A, B, C. And now we turn this around, go back to the definition and say that C, A, B, C is the derivative here by Xi, by the eighth derivative in Xi, the B derivative in upsilon, and the C derivative in zeta of the logarithm of the moment generating function. And as a development point, we have the same as 0. So now by this modification, we come to a new set of variables which have the name cumulants, that are, by definition, they have this property that they factor, and so they will be independent of each other. Yeah? So they have the properties that we have been looking for. Okay? So, and now everything that we want to do is just use our usual MRT with these new variables. So they have solved these two problems. They are independent variables, but they are not correlated. And they are Galilean invariant. At least to the extent, of course, that is possible with the discretization of the space that we have, right? Okay, now, very well, we have this strange theory, and then we come to the how to compute the cumulants. And I have to, because this is, I mean, I know the very best the history of how all of this worked, and I was. So it's very funny. So people told me I was talking about cumulants for 8 years before I actually published a paper on it. And I was talking on conferences, and the thing is apparently so abstract that nobody ever tried to steal it from me. Yeah, so there's so many things get stolen, but this was not stolen. Was not even stolen, which does not mean it is a bad idea. So the paper got 400 something citations. The thing is, cumulants are not easy to calculate. Yeah, maybe we have a look at this later. So there's a lot of different troubles. So first of all, it is not very straightforward actually to come up with an equation to calculate them in the first place. And then when you see the equation, then you notice that it's not even simple to actually calculate this equation for numerical reasons. Yeah? We come to the numerical problems in another lecture. Today we just talk about the theory. So let's see how do we compute what is the computation of cumulants. So I remember looking in a book by Gardinger on the subject back then when we had this idea to use cumulants, and I always remember what was written there is that in the section of the book where they write how to compute cumulants, they start is with there is no easy way to compute cumulants. Okay, so let's see how we can actually compute them. Going by the definition, C0, I mean, like you see, it's d set the logarithm of the, cumulants are the coefficients of the series expansion of the logarithm of the moment of the Laplace transform of the velocity distribution function. So how do you compute these? So you take the derivative, so C001 is obviously the zeta derivative of the logarithm of the Laplace transform of f at the position that zeta, that xi is equal to 0. So the one thing that helps us is that we can simplify this using the chain rule. Yeah? So always you have to think about the chain rule in computing cumulants. Namely, the chain rule will apply to the logarithm here. Yeah? So if you apply the chain rule to the logarithm, you get from, the logarithm, so you have the outer derivative is 1 over f. Yeah? And then you get the inner derivative, and this is d set f, and you remind, so this again here will stay 0. So instead of now trying to take the derivative of the Laplace transform here, instead of doing this, you notice that there is d set directly on f. And from this you know that this is a moment, right? This is the definition of a moment. The derivative of the derivatives of the moment generating function. It's M001.
Right. Yes.
It's M001. Yeah. So it will turn out as M001 divided now f at f itself at xi equal to 0. Yeah. Is the is M000. And this is, you guessed it, it's U set. So by the way, our moments, because our moments were not normalized, yeah, our moments were extensive quantities. We got the momentum as the first moment. Yeah, so this is the momentum. M001 is the momentum. The cumulants are intensive quantities. Because you divide by M00, you get the velocity.
Okay.
It's not the momentum, it's the velocity that you get out of cumulants.
But just to see if I understood, this M000 was to normalize, to call it some, or such as we did with the moments.
So you can normalize the moments. I mean, I did not try to normalize anything. So this the cumulants normalize themselves. Mm-hmm. Yeah? So I did not attempt to normalize anything.
Just then I didn't get where this M000 comes from.
So this is, okay, so if you take the zero derivative of f, yes, and you evaluate xc equals to 0, then you have the 0 moment.
Okay.
Yeah? So, the next thing, C00 was time. Okay, I will take over time again, but anyway. So take this as the second derivative of the logarithm of f in xi is equal to 0. So now again, chain rule, yeah? So what you'll end up with is d set f square actually divided by f square plus d set the second derivative of f divided by f. and all of this evaluated at xi equal to 0. It's again snowing heavily here out there. So now this guy here, dzf, you know, this is again the velocity. I mean, this is the same thing that we had here. Yeah, so we divide now by f squared. So it's again the velocity, but it's the velocity squared. So we'll end up with uz square plus, back here we have the second moment m002 divided by m000. Okay, and if you do this for the other directions and you do C00 equilibrium plus C0, I mean, you put the equilibrium into it, what you'll end up with is this here. You get 3 times theta, which is the temperature. So it's not the energy, it's actually the temperature. It's directly the temperature. So what is so cumulants, if you think cumulants are something abstract, you have to notice that cumulants is something that people know forever. Yeah? So cumulants directly, the first cumulants are the velocity. It's much easier to understand what is velocity because the velocity is something that you can see. It's much easier to understand what is velocity than what is momentum. Yeah? And it's much easier to see what is temperature because you can feel it. So you actually get physically meaningful stuff out of this. Yeah, it's not some abstract energy, but you get something that you can feel. You get the temperature. The temperature is a cumulant. I mean, this is the most compact definition of what is temperature. Take your little brother and explain what is temperature. It's not so simple. So interesting thing is that the equilibrium of all the higher order cumulants, because they are not allowed to depend on anything, and because they do not depend on anything, they just vanish. So it means that the higher order cumulants are 0. Yeah, all the higher order cumulants have 0 equilibrium. Okay.
Could you please repeat that? Of all higher cumulants.
So higher than second order. Yeah. Okay, let's talk about cumulants in terms of central moments. Okay, we do. Now I noticed that nowadays students don't learn a lot about Laplace and Fourier transform anymore. At least this is what we observe with the civil engineers. I hope since you are in CSE, you are very familiar with Laplace transform and Fourier transforms. Yeah, they're very important knowledge. I'm always amazed that everybody talks about convolution neural networks, but do they actually know what convolution is? Yeah. Because, okay, so we have to use a few properties of these integral transformations. Now, the change of frame of reference, according to the translational rule, I mean, it's easy to derive, to see why this is the case if you write it down, but let's just assume that we are all familiar with the rules of the Fourier or the Laplace transform. Laplace transforms. Okay, so if you do a translation in the Laplace transform from an Euler to a Lagrange frame, or if you do a shift in the coordinate system in a what am I doing? If you do a shift in the coordinate system, the shift of origin in a Laplace transform, what you do is you multiply by the shift, by e by the power of the okay, you have seen this rule probably. Yeah. So the only thing is because we have the inverse Laplace transform, the sign convention is different from the usual Laplace transform. Yeah. So here again we have the sign convention. You're moving in the opposite direction. Sign convention opposite to standard. To the standard Fourier transform. Because what we are actually using is in standard nomenclature it would be the inverse Fourier transform. So we have C, A, B, C. So now we get all these derivatives. B, zeta, C. So and now we take the we take the logarithm. We take the logarithm of f with this snake on top, e u. So this moved around, and this in c equal to 0. Now, because this is in the logarithm, you immediately see what happens. Namely, that you get that B. So the logarithm of a product, yeah, this is what we have been using, becomes a sum, and then you take the logarithm of the exponent, yeah, which gives you u times xi. And now you notice that this is a polynomial of first order, where you are taking the derivative of this. So this is non-zero only for the first derivative.
Yes.
Yeah, because even for the zero derivative is 0 because we put in 0. Yeah. So then this will only influence the first cumulant. All the other cumulants do not depend on the frame of reference. Yeah, so this is why they are Galilean invariant. So the only thing that is depending on the frame of reference is also conserved. Meaning that, this is how we designed it to be, and of course it turns out to be as we designed it, all but order 1 cumulants are frame independent. Which of course means that everything you state in terms of cumulants automatically is Galilean invariant to the extent that you can control your cumulants. So now, since it does not, the cumulants do not care in what frame of reference they are written, it turns out that it is more efficient to write cumulants in terms of central moments than in Ra moments, as we will see in a minute. So writing in terms of central moments is more efficient than in terms of Ra moments. And I mean, like by a long way. So, I mean, it's not so obvious in terms of the low order cumulants, but there it's easier to actually write them down. Say we're talking about C002, then we get this to be M002 divided by M000 minus M001 squared by M000, right? And this cumulant has to be the same in whatever frame of reference. So we can write the same equation in the centered frame of reference. So we can write the same thing with K, just replacing M with K, yeah? Because it is not depending on the frame. So it's K200 divided by K000 minus K001 squared divided by K000. So why can we simplify this? Because we said by definition, this thing is 0. And this means that we can always eliminate these guys as being 0, and what we end up with is this is K002. So it's basically the same thing as the central moment is just normalized. Okay, running over time for the lecture already, but we wanted to solve our problems and see whether that we discovered the previous lecture last year. Let's put the cumulants to the test, whether they actually do what we try to solve ad hoc with this weighted orthogonality. Yeah? So let's recall the problem that we observed. Recall problem with the moment M211, which was, of course, a problem of D3Q27, you remember? And we made the discovery that we would have either overdamping or instability with this guy. So we had overdamping in, if you use non-orthogonal moments, and we had instability if we use orthogonal moments, non-weighted orthogonal moments, and we got better results if we had weighted orthogonal moments. So we had to change this little bit ad hoc without good explanation to N210. So we had to basically compute this moment and then relax this moment. Yeah, you remember. Okay. So what if instead of this we use cumulants? So this weighted orthogonality was better than the non-weighted orthogonality, but it was, of course, not Galilean invariant. We did not check whether it's Galilean invariant, but it was not Galilean invariant. Yeah? So the cumulant is Galilean invariant, so it will not be the same. But will it be the same in the same frame? Yeah? So I mean, this here, of course, only works in the non-moving frame. Yeah? So that's what would the cumulant do in the non-moving frame? Let's see. So C211 is, if we write it down, is the K211 divided by rho minus K200 times K011 plus 2K110 times K101. So this is how the cumulant is computed, and then we have to divide this by rho square. So the problem that we observed in the analysis was at second order. This is why we'll now write down this, simplify this guy here to second order. At second order. Okay, let's write it in second order. C211 in second order is K211 to second order divided by rho to zero order minus, okay, now it's a little bit to write here, K20 to second order times K011 to zero order. As you notice, this is 0, K200. Now they could also be two, both of them could be of first order, which I hope, if you listen to me carefully, you already know that this is of course impossible, and they are second moments, they have no first order term, plus K200 to zero order, K011 to second order, and I have to continue on the next page, plus 2K110 to second order, K101 to zero order. Now you notice this will not, this is constant, so it will disappear to K110 to zero order, made a mistake here, K10 to second order, plus again these guys here to first order, which of course, yeah, so you notice that this here cannot exist, this here cannot exist, and this here cannot exist. Divided by rho to zero order square. So of course K110 to zero order is equal to K10101 to zero order is 0. K200 to zero order is not 0. This is theta rho to zero order, and K11 and the other one to the first order is also 0. So what we end up with is that C211 to second order is equal to K211 to second order. Now this is now normalized by rho 0 minus theta K011 to second order rho 0, which means, see, to second order, the cumulants give the same thing as the ad hoc solution that worked, right?
I have a question.
Yeah.
Could you please repeat why those last ones can't exist?
K1,
K110,
so they need to be constant. So this is the stress. They have the stress. The derivative. So the first derivative of a first order value of velocity, yeah, cannot exist. Cumulants remove MRT problem. Which means we have both Galilean invariance and we have the free choice now of relaxation rates. So, okay, guys, I hope you became accustomed that after the lecture we usually continue with some exercise. Yeah, because I guess you may be interested or maybe not. Yeah, so up to you. But we want to see how we implement this in in our sorry, that's the wrong one. In our demo code. Okay, I guess you see it. By the way, as I said previously, the way you implement the Cumulant method is so that it actually works in practice is a little bit different, because you also have to care about numerical properties of cumulants and not only about the algebraic and analytical properties of the cumulants. Yeah? And it will probably come a little bit clear just from this 2D example where the problems originate from. And now you have to remember that cumulants in 2 dimensions are so much more simple than in 3 dimensions. Yeah? So, and it will, okay, let's just have a look. So going back to the code and taking, well, I have to modify my setup here. Let's see. So, okay, going back to the code and just taking the non-orthogonal version of the collision kernel and making a copy out of this. So I always just, okay, this is not the, okay, no, this was not the last one. This is, wait. Try to take the last one. By the way, this is not an efficient way for programming. This is not how you, I am not teaching programming to you, yeah? So it's just seeing through this a little bit. So, okay, let's take this and say we call this run Cumulant, yeah? So now we have a few things that we have to do, because all of this here are the moments, these are raw moments. We've calculated this in raw moments, and instead, so what we should actually do is calculating the central moments to begin with, but because we are just checking things out, what we'll do is we use our binomial transform, yeah, to get the moments in terms of the central moments in terms of the raw moments. Yeah. So I guess we do not need these guys here, but what we need is the central moments. And let's start, okay, let's make a, let's write, we do central moments. Okay, central moments, and the first central moment we have to, no, we call this K02. Okay, so unfortunately I tried this out before, and this is why my computer already knows my variables. Yeah, so K02. Now we have to take this from the, so this is something that we can directly take from the lecture, right? So this is M20, and there in the lecture we've just written that this is M20 minus UX squared times rho, right? UX, so we have to X, Y, so and this in square, and this times rho. Do I do this correctly? So, and the other one is, yeah? Oh, it is Y, it is Y. Oh, yeah. Okay. Ah, woo. You know, it's always troublesome that you know, it won't run, and what is the problem? Okay. So then this is 0 to, so always, you guys watch that I don't make a mistake, yeah? So now it's x. So the last second moment is 1, 1, which we also had in uy. So, okay. Now, I guess we also had in the lecture the third order moments already, or what we could do. Okay, let's do the following. Yeah. Okay, we have. Oh, this makes me nervous. Activate. Okay, so this is the mathematical nodes. So what we use Mathematica to make our binomial transform, right? So we write the function, let's say B trans, yeah? So we want to have a moment A and B, yeah? And we define this as, let me do, so it's the sum over the binomial. So this is something that is implemented in Mathematica directly, so I don't need to do this, and let me write it A and AA. So what I had as alpha, I will call AA, right? Times binomial B and BB. Okay, so, and then there was this times -1 by the power of A minus AA plus B minus BB. So this was how we wrote it. And now this comes into the moments, say M. Okay, so M with the AA and BB times UX, X and Y by the power, no, not here power, oh, what did I do? What did I do? By the power of A minus AA, right? A minus AA, you are always watching whether I'm doing it correctly. Times, times UY.
Shouldn't there be a row divided by M0, 0?
So yeah, it's the moment. Yeah, the moment divided by rho is the velocity.
Ah, yes.
Yeah.
Yes.
So you X and Y by the power of B minus BB. Zip. So, and now we sum over two things. Here we sum over AA from 0 to A, and we sum from BB from 0 to B. Okay, let's see. So then we would have B trans. Okay, let's see whether we got the other one correct. Okay, so okay, I mistyped this. Binomial. I mistyped this, and it is complaining that I try to use X and Y, but I'm ignoring this complaint, right? So now I notice one thing, that will end up with this M here, which is the velocity. So I should replace this. Because this guy here could also become the velocity, yeah? Okay. So I'm going to replace these velocities as, no, they are not velocities, they are momenta, right? So I'll replace momenta 1, 0 by U, X and Y times rho X and Y, and I'll do similar something. You see, the trouble is that they try to help you, and they are not helpful by helping you. So let's also do this and y. Okay? So let's see again. Okay, it also has the 0, 1. 0, 0. Ah! Rho x and y. Not that way. Okay, so you know, I just ignored that it's complaining. It gives the right result, right? So now what we wanted to see is the third guy. Right. So we get. Okay. So we still have these two guys here to replace. Okay. Now we implemented this. Let me see. But we want to express everything in central moments now. Yeah. So this is why I suggest we do the following. We define Ks is okay. We solve for a list of stuff. So we solve for K11. K11 is the B trans of 1, 1, right? Yeah? Plus, we also want to have K, yes, so we want to have K20 as being the B trans of 2 and 0. And we want to have K02 as being the B trans of 0, 0, 2. Yes. So, and then we want to have we want to have these moments M2, 0, because these are the guys that we don't know. M0, 2 and M1 and 1. So let's see what comes out. Yeah, now we have these. Okay, let's now take the B trans here. And do the replacement with with these results, and probably I just take the one this in order to. Okay, so there's K20.
Because the B trans was 2 and 1, right? But shouldn't it be, because here we have M2, 0, and then we would need to do B trans of 2, 0, 0, 2, and M1, 1 of the result. Or why using B trans 2, 1?
B trans, because we wanted to have the third order moment.
Okay, yes, I get it. So, okay.
Yeah, so, okay, so unfortunately we cannot plug this directly in I mean, we should try to, I don't know whether this is, you see, it's getting a little bit longer, but let's see whether we get, we get it a little shorter, but in C++ we cannot easily use this square. This is why we use this we use this A. Okay, let's say we have an A square. We are going to replace this by hold form A times A, right? So in order to split this up, yeah? And then we do C form in order to get this in the format that we needed. I would actually prefer to get it in one line, which they just don't give me. So, and now I can just take this and copy, right? Don't think, just copy. So it's, okay, think a little bit. What was it? It was 2, 1, right? So 2, 1. So float K21 is equal to, so, and now we have this strange subscript thing here, which with a plus in front. Yeah, so I'll write here M, so this is actually the moment M21, yeah? Yeah, so I'll delete this and I end the line. Okay, then the same thing, so it's always good to have things prepared already, yeah, because now we can simply calculate 1, 2, zip, and get this guy out, and we'll again do it, we just believe it. Believing in computers is very dangerous. Float K12 is equal to this guy, and here we have again this M12 minus, actually is transformed in a different format, but hopefully, see, it looks strangely different, right? Okay, let me see. Does it make sense? So it's 2 minus K. Okay, this is not the most elegant way of programming, yeah. But let's just keep going and hoping for the best. So, because we are missing one guy, and this one guy that we're missing is the first order guy. So, how will it look like? Okay, so it needs to have yes, but it has okay, we have okay, so okay, what I'm going to do, I have not done this here far enough, right? So I will just continue. I'll just continue this, saying I want to have this and this in addition to them, right? So then we have M21 and M12 1, 2.
Does it matter the
The order, no. No. Okay, I have this matters. Yeah. Okay, now we'll have more of them. Now let's see what, and okay, now we get something that looks similar to the above. And ugly or not, just copy and paste. Just copy and paste. Zip. Float k22 equal to zip. So then we have here subscripts blah. This is M22 here. This is what it did not properly translate. Okay? Now we have all the central moments, but this is not what we want. We want to have cumulants. Now if you listen to the lecture correctly, then you notice that the third order cumulants and the no, their equilibrium is 0, but to the third order the cumulants and the moments, the central moments, are still the same. Yeah? It's just, they are just, okay, let's save this and see how do we compute, how do we get actually to the moments, to the definition of the cumulant. So the way I do it, is that I take that I let Mathematica get me the chain rule, right? So say we have this function f, which is of x, y, and z, which now would be upsilon. Yeah, I mean if you want to have it in, let's.
But we can, in this case, we can have just 2 variables, right? Instead of 3.
Yeah, because we have to take. Okay, we have, yes, we are in 2 dimensions. You're right. So, and so what, for example, we want to have it in. So this would give us here the first moment, yeah. So first moment divided by the 0 moment. If we are interested in what is the second moment, see, we would get this guy, yeah, where we said that here this here would be the velocity, and in the central moment this will disappear. Yeah, so we can write that in terms of central moments we don't care about this guy, so we'll set it to 0, and we'll also not care about the other one, so we'll also put this to 0. Yeah, and so, and now you can look at what is the third order moment. I shouldn't have used this. You see, the third order moment is still only, the third order cumulant in terms of moments is just a normalized moment.
Okay.
Yeah? So, but the one that is still missing, okay, so then we just use the we just relax the central moment instead. But the ones that we still have to check is the first order guy. So, and the first order guy is not the same. Yeah. So what we get here is this. Okay, So by the way, we do not need to normalize necessarily. Yeah. So I'll just take a non-normalized cumulant, and so this I will not translate further. I will write this in terms of float C22, yeah, and say this is now a non-normalized cumulant if there is such a thing. It's K22, and then it's minus K02 times K20, yeah, divided by rho, because there's rho square. So what I said is minus K02 times K20 divided by rho x and y. And then there is minus 2 times K11 square. Minus 2 times K11 times K11. And again, we have to divide by rho x and y. So now we've turned everything into the format that we need. No, not really. There's one. Okay, so there's still something missing. Namely, we want to do what we previously had as being P, X, X, and E. Yeah. So this we still have to do, saying that there is a K20 minus K02, so notice that I've already done this and say this is K20 minus K02, and we also have to have the sum, which is then the pressure, is K20 plus K02, which is K20 plus K02. Okay? Everything fine so far? So, and now we want to relax these guys. Yeah? So now instead, okay, so the second order, the cumulant and the moment is the same. Yeah? Just that, as you know, as you noticed, the equilibrium here will disappear. So then this guy here is now actually becoming K20 minus K02, and this is again K20 minus K02, still omega. So all of this disappears. What is left is here again K0. You see, there's not a nice way of writing things down. Yeah, so if you implement it, do it more nicely. Now the plus part. So unfortunately, this thing here was somehow scaled, so we have to so we still use, this is still OP, yeah, so it's about the pressure. So here the equilibrium is not zero. Here the equilibrium is not zero. So what is the equilibrium here? So each of them has theta times rho, yeah? So there's this twice, so it must be two thirds times rho. This is what they have as equilibrium, right?
Yes.
And then there is, as I said, the higher order guys, they conveniently all have equilibrium 0. So I just write K, so, and now here comes the first order guy. First order guy, again, is a cumulant, so it has equilibrium 0.
I just have a question.
Yeah.
We saw that the 2-0 was 3 times theta, right? Or 3 times the speed of sound.
This was in 3 dimensions,
Okay. Yeah,
because you add up all 3 of them.
Yes.
So it's in 2 dimensions, it's 2 times.
Okay.
Yeah.
I get it.
So now these guys are here somehow no longer correct. So what we have to do is we have to do the back transform now, since now we have post-collision moments. Yeah. So we'll have to back transform stuff, and the thing that we have to do first is to get the moments K20 back, and this moment K20 is basically K20 plus K02 plus K20 minus K02 divided by 2. Yeah, so this is just the transform back for this. Yeah, and the other guy is the same thing, just with the minus here. So, and now we have to turn everything else back into their. Okay, so one thing that we also have to do is we have to turn back the central moment, this guy here, into the central moment. So we'll do this by putting this on the other side, K and C, and we'll change the sign here. Now we have it back in central moments. Now we have everything in central moments. Now, after having everything in central moments, we have to do the back transform. So, back to raw moments. Right? So, okay, how do we get... So we need to do this here in the opposite way. Back to raw moments. Okay, so first of all, get rid of this. We want to have a moment, and this means we change the sign here. So we just put this on the other side. So unfortunately, on this computer there is no tools installed, so I have to type everything by hand. K plus K. Okay, now I have to be careful here because I have to. Okay, this is very dangerous. So there was a minus here before, right? Okay, so because this is so dangerous, what I do and I don't want to mess it up, I just put a minus and make a bracket. And the same thing here, yeah? Minus, brackets. I mean, I hope I did not mess this up because it looks so different, but sometimes Mathematica just does it like this. I will do the same thing here, M, K, I'll put a minus here and put everything into brackets. Just because I'm lazy and it's 12 o'clock and usually I would have lunch now. So, now we turned everything back into raw moments, and the raw moments will transfer back into populations. Okay, let's see whether we get this thing compiled.
The interesting thing is that in 2 dimensions there was only one cumulant.
There was only one cumulant, right? Yeah, but this is very different in 3 dimensions. Yes. Well, everything above the third order.
Okay.
So there will be how many? There is how many first order moments did we have? We had 3 of them and 6. I think we have 9 first order moments. And 3 fifth order and 1 sixth order moment in the D3Q. So it's a really big thing. So, okay. Wait. We've forgotten something very important. This function cannot be called. Okay, let's do the interface. Let's do the interface. Call this Cumulant. And calling Cumulant. So, okay, do it again. We still have 1 listener from the internet. Okay. I mean, now we can completely. Okay, I tried out this yesterday in the evening. I played around a little bit and put this to the relaxation rate to 1.999995, right? So let's restart the stuff and call this with run MRT weighted orthogonal, right? And everything with 111, yeah? And go down here. Wait, I need to have more space, I believe. Go down here and see whether whatever this does. Okay, so we have very high Reynolds number, supposedly. Okay, we don't get the entire thing on the screen, unfortunately. Oh, it kind of works, right? Yes, so I did not calculate the, you can calculate the Reynolds number as a homework. So it's generating a lot of small vortices here. So this is the best code that we had last year, right? It's amazing. It works. It works.
But this one is using which one?
No, this is using the weighted orthogonality, the weighted orthogonal MRT. Oh, I hope. Well, actually, I would have preferred that it crashes.
It should crash.
I mean,
I tried to run this same one when
Okay, it crashed. Okay, now it crashed. Yeah, let's. Okay, now we may missed. So it makes me nervous that these two equations did not look the same when we put them out of Mathematica. So I have no idea. Cumulant, or did I call it cumulant or cumulants? Cumulant. Okay, let's try to run it with cumulants. Oh, immediately crash. Okay, so we did something wrong. If it crashed so quickly, then we did something wrong. Okay, so let me see whether this is a problem that we can easily fix. Otherwise, we are in big trouble today. Okay, now you have to help me finding the mistake. Where okay, let's go from the beginning.
The first thing I have a question of is why is there a row in the M2? Could you please go down?
Down.
Yes, they're in K20P.
Can you give me the line?
It's 472.
72.
Why was there a row there? Because here I have that K20 is
The zero moment.
it's the sum, and in the end it was 3 times, or in 3 dimensions it was 3 times theta.
Yes.
But there was no row, and now we have.
Because the cumulants are normalized.
Okay.
Yeah. So here we did not normalize.
Oh,
Okay.
okay.
Now. See this? Oh my God! I did it everywhere. Oh my God. So this, of course, needs to be the central moment. Yeah? You know what's the good thing is about this? You now notice that I did not cheat, right? Because if I compiled the code that I've written yesterday evening, well, then it would have run. Okay, I miss you. Of course, we have to take the non-equilibrium from here. Okay, let's restart everything. Did it actually restart? And run. Oh, it runs. Okay. Let's see what happens. You see, it is in that sense more stable, as the other version already generated a lot of vortices here. What you notice is that it does not, but this was the case in the other case too, that it doesn't really like the boundary condition that much. Yeah. So you see some oscillations in the boundary condition. But it did not generate these micro vortices directly in the corner in the beginning.
And is that?
So now it generates micro vortices here.
But the interesting is that totally different than the other ones.
Well, the other one crashed. Well, yeah. So you see, they're very, very low viscosity, yeah? So this shear rate, so it's shooting down here, yeah, with very low viscosity, yeah? So the vortex goes around here, it just shoots, and there's very, very little interaction with the surrounding fluid because it has low viscosity.
That happens because it's 1 omega.
No, the omega is very close to 2.
But weren't there used 1? Can I?
So you mean for the higher order moments?
Yes, because that happens. I think that happens because it's 1.
Okay, so what do you want to see?
The 1.999.
Everything, but then you're doing BGK.
Okay. Why? Because it's the same.
Yes.
But maybe just 1, 2
So then it's no longer BGK, but then it may have the same problems as BGK.
Okay. So the thing here is to have one, or they all have to be one.
No, they don't necessarily all have to be one. They can be different. I don't know what you want to see. So it's
because if they are one,
I put them to okay, let's try out. I have no idea what happens now. I put 1.2, 1.3, 1.4, okay? So it will probably be less stable now.
I understand. That was the beginning of this lecture, that there was one problem with the...
Yeah, if you don't put them the same, but you see now we have the vortices going off a little bit earlier, yeah? Apparently. Okay, if you complain about that it's being not the same, is that of course if you put such a low viscosity, it implies that the simulation is under-resolved, and then it's very difficult to say what is correct and what is not correct.
Well, I'm not saying that it's not correct. It is just that, or what I think is that there are other assumptions, or there are like, in using cumulants, something is implicit. Because when, for example, taking the M11, when M11 is 1, or
The M11, no, M11 is not 1. M11 is the viscosity is governed by the BGK relaxation rate.
Yes, for example, well, the moment, the M11, if the omega of M11 is 1, that means that M11 is going to be the same as the equilibrium.
Yeah, but this is not the case.
Yes, but the interesting thing is that when M11 equals to the equilibrium,
No.
that's or we see it's not the same. We do not see these vortices, but it's the velocity is going to draw this square.
No, this is the reason why we see this, as you say, square, is because the viscosity is very small. Yeah. So there is a jet going along the wall that has basically zero diffusion, so it does not interact with the fluid because the viscosity is very small, and you have a jet, yeah, going along the wall. There is no interaction between the fluid and this jet because the viscosity is small.
Okay.
So basically, of course, you would see some turbulence which you do not see because you don't have enough resolution. Yeah, yeah. This is why it's probably not physically correct, but it is correct that there is very little interaction if the viscosity is very small because there is no diffusion of momentum.
Yes. The interesting thing is that with cumulants it happens.
Yeah, but this is correct. Okay, yeah, so interesting. Still, I'm not completely alone here, but basically, I don't know. We could now compare these two things. Yeah, I suggest that you play around a little bit with it and see whether there's differences. And other than this, we'll see each other next week. Yeah. And thank you for joining in.